So we just finished watching this movie here about how small atoms are, right? Tiny, tiny little things, right? I'm going to give you a couple of more examples of how small they are. A couple more of these kind of visualization guys. So, golf ball, right? If this was the size of the nucleus, we cool? Take the nucleus, blow it up as big as this golf ball. The first energy level, remember our energy levels that surround the nucleus? Take a guess how far away it would be from this nucleus this size. No, not quite that big. It'd be from here to, if you go east on 198 to the cemetery, from here to there, that'd be how far away the first electron would be. It's a long way, right? If you're going the other direction on 198, it'd be past the little convenience store with the lights on the outside, right? That would be how far away it would be. The second energy level would be past Burtonsville. And if you're going toward the church, it would be past Spencerville Church, going the other direction. It's a long way away. How about this one? If I say an atom is as big as a basketball, right? I blow it up this big, we cool? Then the atoms in a dime are now as big as the entire Earth. Oh, sure, atoms in everything. I'm saying if I took every atom inside this dime and blew it up as big as a basketball, right? So now every atom is as big as this basketball. This dime would now be as big as the Earth. It's huge, right? These atoms are tiny little things, right? It would be even way smaller than that. Remember, if you had to make a blueberry as big as a football stadium to make the nucleus as big as a marble. Are we cool? My point is this. I'm not asking you to memorize this thing. Are you comfortable that atoms are small? Okay? That's the whole point behind giving you all of these examples. Atoms are tiny little things. But here's the problem. We as chemists, what is it that we deal with? Atoms, right? That's the whole point of interacting them and putting things together and making new stuff. We're all reacting and doing stuff on the atom level. But we can't see that far, right? It's too small. We can't, with our naked eyes, see that. We have some instruments that help with that, but we can't do much with that. Are you cool? So what we have to do instead is we make a group of atoms. And we talk about this group of atoms. And you use grouping all the time in your life. Let me ask you this. If I say that you have lived 1.5 decades, how long have you lived? 15 years, right? Because we know that a decade is 10 years, right? If I say, go get me a dozen eggs, how many eggs did you get? 12. For a dozen donuts, that'd be better, right? But a dozen means 12, right? If I say that you will remember me for centuries, how long is that? Hundreds of years, right? And a song as well. We cool? Sorry, it's bad. I have to sing it. No, but it's terrible, terrible, terrible. All right. So what we use in chemistry, we use something called a mole. A mole in chemistry is our counting group. Okay? And because chemists are lazy, we cannot write a 4-letter word. We have to abbreviate that as mole. I'm not joking. That's really the abbreviation. So if you see something as 6.4 moles, they don't write the E. I don't know why, but we just don't write the E. Okay? So moles are our counting group. Like a dozen, like a century, like a decade. Moles is the counting group for chemistry. But do you know how many pieces are in a mole? Anybody got any guesses? 7? No, much bigger.
30.
How many particles, let's say how many atoms do I need to make up a mole of something? 30, way higher. 6 million, way higher. 6 billion, way higher. Whew, quadrillion, way higher. Whew. You ready? Here it is. 1 mole is equal to 6.02 times 10 to the 23. If you want an actual number, 602 sextillion. It's well done. Okay? If you want to actually write that number, it looks like this. 602, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's how big that number is. 602 sextillion. So if I have a mole of air, I've got 602 sextillion molecules of air. We cool? If I have a mole of water, I've got 602 sextillion atoms or molecules of water. Does that make sense? That sounds like an awful lot, right? You see this? This little water bottle, this tiny little water bottle, that's about a mole of water. It's not very much, right? No. But again, remember, atoms are small. So when I put a whole bunch of a very small thing together, I still get a decently small amount. Yeah, this is about 250 milliliters. It's a little bit more than that, but it was a good visual. Yes, sir. But why do you care? It's good. Because as chemists, this is what we use to actually figure out how we're going to make stuff. Okay? So for example, David comes up with this new drug, this new compound, that if you take this, you become the best basketball player in the universe. Right? It's like the stuff that's in like Space Jam, they drink it, and they're like, oh, we're huge, we're big, right? Okay? We good? But he needs to know how much of each ingredient does he need to make his compound, right? Because again, everybody wants to buy this stuff. So as a chemist, you have to use these tools I'm going to teach you, or what we call stoichiometry, in order to figure out how much of each piece you need, like a recipe. Does that make sense? And I have to tell you this, my friends. Of all the stuff that I teach you all in chemistry, this is consistently the one that when my students come back to me after they go to college, they say, I'm so glad we spent the time we did on this, because I have to know it. I'm teaching now my friends in college how to do this stuff, okay? And don't worry, it's nothing but multiplication and division. There's nothing more complicated than that. We cool? All right. So, by the way, this number here is called Avogadro's. Don't know why this is here, sorry. This is Avogadro's number. Avogadro's the name of the guy who came up with it. It sounds like avocado, but it's not. It's Avogadro. Yes? So is that the number of atoms? Right, so this would be 6.02 times 10 to the 3, and it can be anything. It can be particles, it can be atoms, it can be rolls of Clorox tissue, right? It can be books, it can be Richards. It'd be weird if we had a mold of Richards, but we could, right? So it's just a group, it's a grouping, it's a counting group. Exactly, exactly. Sir? Why 6.02? That's a great question. Your textbook, by the way, if you want to go with me, I am in chapter 10.1. That's where we're starting on today. On page 321, they give you a more detailed number. This is a rounded number, 6.02. Can I say we'll come back to that? Because I don't want to go too deep there. But yes, there is a reason behind it. It's not just a random number Mr. Avocado decided he would pick. No. There's definitely a piece there. Okay? So, let's go back to our example of David making his amazing basketball formula. Are we cool? How many moles of this formula would you like to make, David? Pick a small number of moles. 3? Excellent. So David wants to make 3, and I'm going to give you a 3.0, moles of his substance. Are we comfortable? And I want to know how many particles are there. Or if you don't want to say particles, we could say how many molecules. We're going to assume that he's making this molecular substance. Okay? How would you do that, friends? Times 3. Right? Now, what I want to do is I want to show you a little bit of a system. Stay with me, guys. Shh, 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 shh. I want to show you a system. And I use this for all of my stoichiometry. I'll put this word up on the board just so you can see it. S-T-O-I-C-H-O-I, stoichiometry. This is the study of these particles, how we make these conversions between stuff. We cool? So, I do it like this. Shh. I take 3.0 moles and I put it into what I call a skeleton, which is simply multiplication and division, just like a little bars here, right? And what I want to do is I want to get this unit from moles to molecules or to particles. Are we cool? And we know that here's my conversion, that 1 mole equals 6.02 times 10 to the 3. And again, this can be particles, this can be atoms, this can be molecules. It can be anything, right? It's just a counting group. So here's my conversion. 1 mole is 6.03 times 10 to the 23rd. Are we cool? So here's the math. Because I have moles on top, I put moles on the bottom because I want the moles to cancel and leave me with particles. Does that make sense? I want these guys to cancel out. If I take moles divided by moles, it cancels out. Are we cool? Because in units, we can do the same thing as units you do with numbers. You can multiply and divide them. So, if here's my conversion, if 1 mole is equal to 6.02 times 10 to the 23rd, does 1 go down here or does 1 go on top? It's 1 mole, right? So therefore the 1 goes on the bottom and the 6.02 times 10 to the 23 goes on top. And then just like Andrew said so nicely, I simply multiply these guys together. If there were multiple numbers on the bottom, I would multiply them as well, but there's not. There's just one number. And then I divide the two answers. So in this case, it's simply 3 times 6.02 times 10 to the 23 and divide it by 1, which of course is the same number. Question, sir?
Wait, so do you need to put 6.02 or do you put moles there? Because that's like...
What they're saying is in 1 mole, there is 6.02 times 10 to the 3 pieces.
Yeah.
So it depends on which way. If you're going to make them a group, then you would just say, hey, that's 1 mole. But if you want to talk about the individual pieces, you would say 6.02 times 10 to the 23 of whatever they are.
Okay.
I want to make sure that you can do this on your calculator. Can you actually enter in this 6.2 times 10 to the 23? I do not put 6.02 and then the multiplication times 10 and then the exponent 23. That's incorrect. Here's how you do it. You ready? And take your calculator. This will be helpful for you to see. You want to make it 6, and then again the point, 0.2, and then some calculators have an EE button. Some of the newer TIs actually have a separate button that says EE. If not, you'll have to do the second, and then there should be an EE up on top of a different button. Okay? There's also some that have a 10 to the X button. That also will give it to you. But if you do 6.02 multiplied 10 exponent 23, it'll give you the wrong answer at times. Does that make sense? After we finish this, I'll come around to each of you and make sure you're comfortable with the calculator you're using, how to do that. But that's a key piece. So what's our answer here? Somebody got, can you plug this in? 3 times 6.02. And tell me what we get. 6.02 e to the 23.
Just e?
Not the little e. The little e is an actual number. I don't know how to do it with your calculator, my friend. Maybe if you go that way, you'll get more.
Oh, well.
Yeah, it'll be difficult to do. I have to play around with it. Yeah, we have to try it. Who's got a number here? Sorry. Who's got a number? Yes? 1.806 times 10 to the 24th. And what is my units? What are we dealing with here? Particles. I'll say this to you for the first time, and you'll hear me say it many times in the future. Numbers without units are worthless. You have to have a unit to tell me what that number is.
If we don't write a unit, we'll get the point.
You will miss a point, sure. Yeah. Yes, ma'am.
If we had particles on the bottom left, wouldn't they cancel then you wouldn't have units left?
Yes.
So then what would be the units?
There would be none, if that was the case. But that would be moles per particle. That really, we wouldn't have a unit like that.
Okay.
Yeah. Let's do one more, my friends. Let's say instead of David wanting 3 moles, let's say instead he wanted 9.56 times 10 to the 25 molecules. And Ben wants to know how many moles that is. Are we cool? So we're just going the opposite direction now, right? We're starting with molecules, we're starting with pieces, and we're going to moles. So here's what we would do. We'll set up our skeleton again. 9.56 times 10 to the 25 molecules. And again, don't confuse that with moles. They're different. And I'll set up my skeleton. So I'm going to use, again, the same conversion, right? That 1 mole is 6.02 times 10 to the 23 molecules. But what goes on top? Does moles or molecules go on top? Moles. So 1 mole goes there because that's what I want to end up with. And the 6.02 times 10 to the 23, not particles in this case, we're actually using molecules. Those go on the bottom. Again, because I want the 2 units to cancel out. So in this case, how would you plug this into your calculator? Are we multiplying now? No, we're dividing. 9.56 times 10 to the 25th divided by 6.02. Somebody give me a number? So how many significant digits do we have here? Oh, going back to old school stuff. How many? 3. So let's round that to 3 significant digits would be 158. 158 what? Moles. It is, truthfully. Was 158, is that correct? Is that the right number? Okay. No, I'm just making sure. I'm just making sure. Does that make sense, my friends? Sir?
What if the number is smaller than the actual mole, but it's like...
Sure. So you can get a decimal of a mole. You can have a 0.1 of a mole or a 0.001. Yeah, just like anything else. Yeah, it's a good question. Sir? You might do some rounding. It's based upon the number of significant digits you started with. You always want the same number in your answer that you started with. It's good questions. Sir? Right. If you look between this guy, I went from moles to particles, so I multiplied. Here, I'm going from particles to moles, so I divided. And again, I don't want you to have to memorize that. I want you to use the skeleton so you see that. That's the goal. Because coming, just so you know in the future, we'll do 2 or 3 different conversions all at once and get an answer. And if you use this format, it just makes it real easy to do that. Okay? What I'm looking for you to do is in 10.1, this is 10.1, page 323 or 324, numbers 1 through 6. You've got about 10 minutes. I'd love for you to work at it.